Hello and welcome to Learn Data. It's great to have you on this channel. I'm Nilesh, and this video is continuation of the previous video where we talked about the intuition behind whitening or sphering of a dataset. Here what we'll do is look at the actual implementation in Python on using either PCA method or ZCA method to whiten a dataset. So let's get into Jupyter notebook and see how that can be done. Here I have imported three libraries: NumPy, Scikit-learn, and let's go ahead and also import matplotlib. So import matplotlib.pyplot as plt, and these are the versions that I'm using for Python and Scikit-learn. So the very first what we'll do is try a simple example where we have a smaller number of data points, and then we'll use a larger data set. So for this we'll create an array np.array, and we'll have 5 values 1 2 3 4 5, and then we'll have another set of 5 values, so 11 12 13 14 and 15. So as you can see, this the size of this one is 2 by 5. So if you print x dot size x x dot shape, sorry, x dot shape is 2 by 5. So here we are assuming that this row 1 which goes from 1 to 5, that's one feature, and the second row that goes from 11 to 15, that's the second feature. So you have two features in this particular array. Now what we'll do is we need to zero the data set. So for that purpose, uh, the easiest way is to use x. We'll save the zero mean data in xc. So we have x minus np dot mean x, but when we run this, it's going to run into an issue where it will calculate 5 values thinking that each column is a feature, but that's not the case. Therefore I'm going to go ahead and change that. So if we use axis is equal to 0, we get 5 values, and that's not what we need. So to make this work correctly, I'm going to transpose these matrices and then transpose this. So now we get output where we have the mean values for this uh, listed, so centered value for this particular row, and we can go ahead and leave it like this. So we have the centered values, and when we go ahead and and then c dot okay, so now we have back 2 by 5 data set. Next step, we'll go ahead and calculate the covariance matrix. So x cov is equal to np.cov xc, and then row var is equal to true and bias is equal to true. So that gives us the covariance matrix. Next, we'll use this matrix to calculate the eigenvalues and eigenvectors. So w is the eigenvalue, v is the eigenvector. So we'll use the linear algebra library. So for that, let's go ahead and import that as well. Import from scipy import linear algebra, and now we can use linear algebra library here, dot eig and then xcov. So this gives us the eigenvalues and eigenvectors. eign values, and here we can specify w, and then we have print and this is eigenvectors, and here we can specify the value v. Okay, so these are the eigenvalues and eigenvectors that we have found for this particular data set. And uh, the j is for denoting a complex number, but it is 0. So what we can do is uh, for w is equal to, if we wanted to, we can say dot real, and that gives us the values without the j, letter j. And if we round it to, let's say, 4, then we get the rounded value. So that's just a side note there. Now once we have the eigenvalues and eigenvectors, we can go ahead and calculate the diagonal, can create the diagonal matrix with eigenvalues. So here we first need to invert it. So 1 divided by w into raised to power 0.5. So we need square root of w, and now we'll put this in the diagonal function np dot diagonal. So now when we look at this variable, we see that it's a diagonal matrix where off diagonal elements are 0. Next, and the reason why I did not add the 0.1 e raised to power 5 here is just to make it easier to visualize the data when we plot this. The next item that we'll try to do here is calculate the x rotation. So a simple thing to show is how we can rotate a data set using an eigenvector, and this is one example. So if we take a dot product of the vector with our centered data set, then we can rotate it, and we'll plot that shortly. Now let's calculate the whitened values using PCA method. So WPCA is equal to, and if you remember from previous video, the formula that we have for PCA to calculate whitened data set is inverse square root of lambda, that is the eigenvalues, dotted with transpose of eigenvectors, dotted with the data x. And here I will use the same method. So first we'll dot np dot this would be the eigenvalues. So we already have the diagonal values calculated. Then the second one is v dot t, so transposing the eigenvector matrix, and then we are going to use the resulting matrix and dot that with xc, which is our centered data set. Now for zca, we will use the same method. Here the formula would be this: eigenvector dotted with the inverse square root of eigenvalues, dotted with the transpose of eigenvectors, dotted with the data. And so for that we'll begin from the innermost part. So np dot, and here we have the value of v dotted with diagonal w, and once we have that, we can use the output of that to dot with v dot t. So that is the transpose, and then finally we have the xc np dot. So these three are the values. Now we'll visualize how each of these look. For that we'll create scatter plot. So plt dot scatter, and we know that our data set has the values, the features in rows, not columns. So we'll use that. So for row 0 all columns, and then xc for the y value will plot row 1 and all columns. So that's how our data set looks like, the original data set. And what we have done next is, so this is our, so let's look at the data set that is not centered. And as you can see, the blue dots are the not centered, the original data. Orange is the centered data set, which is at 0. So we'll continue working with the centered data set which we have, and label this. Label is equal to centered, and then we'll use the other values. So the next one is, we'll plot the rotation. So x rot, and this would stay the same, so copy all of that, paste it here, and instead of xc we need x rot, and this will be rotated. So as you can see, when we rotate the matrix centered dataset, it is now shown here by the orange dots. So let's plt.legend, and now we see the dots. So this is the rotated data set. Now let's look at what we see for the whitened data set. So for WPCA and WPCA again, PCA, and then the next one is WZCA that we have. So WZCA, ZCA. So when we run this, now as you can see, we have, so I'm going to go ahead and add a marker here, marker for PCA, and then marker for ZCA, so maybe X. Okay, so that we can see what we have here. So in this plot now, we can see that the original centered data set is these blue dots. So these got rotated on the right hand side, which is now represented by the yellow dots here. And so this is our original centered one, this got rotated there. So this is the rotated data, and once we applied the PCA, we have, this is the whitened data set, and similarly the ZCA is along the original data set. So the difference between PCA and ZCA output, as we can see, is that the ZCA output tends to bring the whitened data set back to how it looked in the original data set, whereas ZCA stays in that rotated position, as we see here. Now moving on, let's look at another example. In this example we had a small data set. Now we'll go ahead and use a much larger data set for 1000 values, and see how we can, if we see any spherical data set formed after the whitening procedure is completed. So for this, we'll create a multivariate data array. So np.random.seed will have a seed of 1, and then mu is equal to 0 0, so that's the mean, and then sigma is equal to 6 5. This is just the format in which we need to input the values, and then n is, we need 1000 data points. So x is equal to np.random.multivariate_normal, and here we specify mu, sigma, and then size is equal to n. So here we have the 1000 data points. So I'm going to go ahead and print shape of x, and as you can see, this is 1000 by 2 matrix. So we have it in a format where it is columns. Each column represents a feature. We are going to change that and convert in such a way that each row represents a feature, but we need this for the zero centering part of the code. So let's do that now. So here, if we have xc is equal to x minus np dot mean of x, and now if we look at print psi xc dot shape, here we can see that we have the 1000 by 2, and here we need to specify axis is equal to 0. So what that does is we get only two values because we have two features, and that's what we get here. And after this we need to go back and flip it to a transpose form. So now when we print xc dot shape, we should get 2 by 1000, and that's because we are going to, for the subsequent code, we have this assumption that each feature is in a row. Now we can go ahead and calculate the covariance matrix. So xcov is equal to np.cov xc, and here we have row var is equal to true, and then we have the bias is equal to true as well. And next we'll calculate the eigenvalues and eigenvectors. So w is the eigenvalue, v is the eigenvector, is equal to linear algebra library that we have dot eig into parentheses xcov. Here we could also use dot eigh, but I've just used the eig. Next we can go ahead and create the diagonal matrix for the eigenvalues. So this would be 1 divided by w raised to the power 0.5, so square root of that, and then we take the np dot diagonal for this, and here again I'm not using the 0.15. If we run into an error, we can add that there. Then we have wpca is equal to np dot dot, and we'll start with the innermost dot product, diagonal w v dot t, so transpose, and then this needs to be dotted with our data, which is np dot xc. So this is the one. And finally we have wzca, which is np dot again we start here, we are going from left to right, so the innermost is going to be diagonal w and v dot t as before, and then the left to this we have np dot v comma this, and then to the right of this we had np dot all of this, and we had xc. So that's our calculated matrices there. Now we can go ahead and plot them and see how they look. So I'm going to go ahead and create subplots. So figure is equal to plt dot figure fig size is equal to, let's say, 10 by 3, and then we have the plt dot subplot. The first subplot we have is going to be just the original figure, so plt dot scatter, and here we have x, and for x in only in this case the features are in columns, so that's why I've set it up like this, where we have all rows and column 1, and then we have x, and second one is all rows, and we have the second column there, and label this as original, and we can set the alpha to 0.5. Next we'll copy this, so to avoid typing, and let me copy again. So now we can go ahead and add the second one, which is XC, that is the centered data set. And for this, we have 0, comma, colon, 1, comma, colon, because from now on we have the features in rows rather than columns. Centered, and we are going to copy, paste twice. So here this is for WPCA, copy that, and then after this we have WZCA, copy that, and finally we have plt.legend. Now when we look at this, okay, yes, one thing we need to do is add a different number for the subplots so they don't get all overlaid. And here we have WPCA, WZCA. I wonder why the labels are not showing up for any of these. Okay, plt.legend. Oh, the reason is because we need to specify that for each of those subplots. Okay, so now we should see them. So as you can see here, we have the original data set, which is looks like it is centered. Of course it is centered because we had set the mu to 0, so that is centered. And then we have the values for the centered data set, it's going to be the same. Then we have the spherical shape of the data arrangement for WPC and WZCA, and that shows the effect of whitening or spearing. We can also go ahead and plot this on the same plot, so let's do that. So you can see the scale and how they look when they are plotted together. So I'm going to delete all of that and change this to much transparent. So here, as you can see, the data points are these, the ones with which are whitened are much compact in the center in shape of a sphere. So why don't we go ahead and change the marker to make it easier to see. Marker is equal to X, and let's change this back to 2.25. And as you can see here, the blue is the original data set centered, and then we have the whitened data set right here in green and orange. So that was it for this video. I hope this was an exciting video for you all to implement whitening or spearing in Python. And building up on the intuition from previous video, we can see that it's not at all complicated. There's just a couple of lines of code to kind of get to the final stage where we have this whitened data set. And again, the importance of whitening or spearing a data set is to remove any correlation that may exist in between features in the data set. If you have any comments, questions, please let me know in this comment section below. I hope to see you all in the next video. Please like, share and subscribe. Thank you.